Now, a general question also is, why is it that only human people are able to speak? So definitely, if you compare us to other animals, it's quite obvious that even our most close relatives, chimpanzees, aren't able to communicate to even the extent of a 2-year-old. Certainly, it has been possible to teach chimpanzees some kind of sign language, and it has been possible to get them to communicate in various ways, but it's still not possible for them to actually be able to vocalize and to use words in the same way that we do. This has led to the idea that there must be some genes which code for our ability to produce language. Basically, that there must have been some genetic mutation somewhere between the lineage leading to us and to modern chimpanzees, which has made some change in Broca's areas and Wernicke's area, which has made it possible for us to produce speech. And one of those genes seemed to be the so-called FOXP2 gene, which was discovered originally because of an English family in which none of the members were actually able to produce language. And it turned out that this family was suffering from a mutation in the FOXP2 gene. And it also turns out that when comparing chimpanzees and humans, that it's the FOXP2 gene which has had much more mutations than what should be expected from the number of years which has happened since the chimpanzee and the human line deviated. So there are 2 distinct mutations which has changed this gene quite dramatically from what is seen in chimpanzees. The problem then is that it's not really clear what this gene is doing. It seems to be a gene which is involved in regulating how much the different neurons are differentiating and how widely the different connections in the brain will be spreading. So if you have less of, or if the FOXP2 gene is not functioning, you simply have a less dense network in your brain, and maybe it is because of this that it's all in the network that the ability of language is arising. It has been demonstrated that if you take the human FOXP2 gene and put it into a mouse, then the mouse actually changes its vocabulary to some extent. It's still basically screaming most of the time, but it's apparently screaming with a higher frequency. So it does also in the mouse affect its vocabulary to some extent, but it's still not really clear in what way. One important thing here is that, and I've in many ways I really like this finding. It turns out that we definitely need to learn language early on in order to be able to master it at the highest possible level. And when we're learning a new language later on, after approximately our 11th year or thereabouts, it turns out that we have to use a different network. So the parts of the brain which is involved in generating our native language turn out to be different from the areas which are used when generating a foreign language. So there is a distinct difference between those of us who are truly bilingual, which means that we have been learning 2 languages before the age of 11, as compared to those of us who have only learned 1 language and then have to learn the next language after the age of 11. So this is a simple sketch of which areas are being involved when people are generating different words, in this case monkey or freedom, either in a foreign language or in a native language. And as you see, it's quite different areas of the brain which are being activated in these two cases. So it's different networks which are being involved. It also turns out that in Japanese you have, I think, even 3 or 4 different alphabets, and you sort of have also almost a different language for women and for men, and those different alphabets and those different languages are being processed also in different parts of the brain. So it's sort of as if there is a dedicated network which is open in kind of a critical period up till the age of about 11 or so, where you can really learn to master a language. Then later on, that network is now dedicated to that particular language. And later on, you have to use different networks in order to learn how to use it. So people who are truly bilingual would have both the so-called native and the foreign language in exactly the same area. There are also other signs that there are some possibilities of plasticity in the language system. This is taken from a monkey which was basically given a banana whenever it became good at finding or distinguishing specific tones. So it was conditioned to listen to a tone of 2.5 kilohertz precisely. And it was basically given a banana whenever it successfully identified this tone. And what you see is that before training, when it was just listening to it without being given any reward, this is sort of the area where you would see activation in its brain when it heard this tone. Whereas following the conditioning and following this 2.5 kilohertz training, you saw a much larger activation in the brain. So you can be conditioned, you can be trained to actually have your brain being better at distinguishing different tones, which also means that is it now really our musical abilities, is that something that we're born with, or is it something that we can actually train to become better at listening and distinguishing different tones? And at least to some extent it seems that there is some possibilities of becoming better at distinguishing these tones. But what speaks a little bit contrary to that is that if you look at musicians who have absolute pitch, so absolute Gehör, who are able to distinguish particular tones by just listening to whatever tone and being able to hear whether it's an A or a C or a D or whatever. It turns out that there are specific differences in part of their brain, and especially in this planum temporale region, which is shown here, which is in between the parietal and the temporal lobe, close to Wernicke's area. You see that that area is actually quite a lot bigger in these musicians. So there are differences which seem to be related, in this case, potentially to a specific gene, which makes this area larger than in other musicians. If we turn a little bit into music in general, which could be fun, but it's not something that we need to do, there is now quite a lot of research which has been done and which has been documenting all of the various areas of the brain, but it's not something that I want to go into in detail, but it's just to emphasize that, again, musical ability, our language abilities, etc., it's a network. It's not just a single area. This is all the different areas of the brain which are being involved, and certainly there are some emotional areas, there are prefrontal areas which are involved in understanding the abstract cognitive properties of the music, the motor areas which are being involved in understanding the frequency, the rhythm, and all of these things. So again, it's a whole network which is being involved in the ability of generating and understanding music. I'm going to skip all of this. It's great fun, but it's not something that I want to go too much into. We have to stick with the language